So equilibrium is all about the ratio. So at the point when a particular reaction is at equilibrium, that means the reactants are forming the products and the products are forming the reactants at a constant rate, and so we set up just a consistent ratio of reactants to products. And so to compare reactants and products, we need to consider a couple things. We need to consider all the players, so all the reactants, all the products. And we also need to be concerned with the balancing coefficients. And so that would be those numbers right in front, the stoichiometric coefficient. So when you balance a reaction, those would be the big numbers you write in the front. And, we saw on the last slide or last video how when you had double of the NO2s, well, the reaction would happen a lot quicker for the NO2s than it did for the N2O4s. And so we do need to consider those balancing coefficients. So step number one, start with a balanced equation. And then we find the equilibrium concentration, which we symbolize with a capital K, by setting it equal to the products over reactants. Ladies and gentlemen, let me say that again. It is products over reactants. One more time, products over reactants. Why do you think I'm repeating this several times? Because everyone does it backwards their first time. It is always products over reactants. Hey, say it with me. Products over reactants. And brackets mean concentration, and so what we're going to deal with here, concentration and molarity. So it'd be the molarity of whatever D is raised to the power of D, and if it's just 1, then it'd be 1 and stay the same. If it was 2, it'd be to the second power. If it was 5, it would be to the fifth power. We multiply it by the concentration of whatever E is, and if there's an F or a G, we add those on as well. Sometimes we would just have D even. And then it's over our reactants, which would be concentration of A times the concentration of B, both raised to their power. And this capital K right here means the equilibrium constant. So anytime that we talk about the equilibrium constant, we're talking about capital K. This little subscript down here, though, can change depending on what it is that we're calculating. So in this case, since we're calculating the concentration, so we're using those brackets, they put a C down there. And so that just means the equilibrium constant based upon concentration. Some of the other ones that you're going to see are like Ka, which would be the equilibrium concentration of an acid, or Kb, which would be the equilibrium concentration of a base, or a more simple one would be Keq, which is just the equilibrium concentration in general. But don't be confused by those subscripts. They're just referring to what system we're talking about. It's always the same thing, products over reactants. So here's an example. Let's write the equilibrium expression for this particular reaction. We have nitrogen reacting with oxygen to form nitrous oxide. So always write down K. So Kc is equal to, and here's another important thing. This may not seem important to you. You might just be tempted to leave that off. Do not leave that off. You have to write the equilibrium constant is equal to and then set it up. And so remember, it is products over reactants. In this case, we just have one product, so it would be NO. And we do put it in brackets because we're indicating we're talking about the concentration of nitrous oxide. And since there is 2 of them, we would square this value. And then down on the bottom, we would do the concentration of N2, and it's only one of them, so it would be to the first power, times the concentration of O2. So when you are asked to write an equilibrium expression, that is what they are looking for, right there in its completion. So you need to put the K, you need to put some kind of subscript, and you need to put brackets around whatever you're talking about if it's dealing with concentration. Don't be tempted to put parentheses. Parentheses do not indicate concentration, so they will not work. That seemed pretty simple. Let's make it a little bit weirder. So solids are left out of equilibrium expressions. That means you need to pay attention to the states of matter. So the reason we leave solids out is because the concentration of a solid is really constant. So if you have a chunk of a solid and you shrink down its size, remember concentration is moles divided by liters. And so if you take away some of the volume of a solid, you're taking away some of its moles and some of its volume at the same rate. And so it winds up that you have the same ratio either way. And so then in an equilibrium equation where we're dealing with ratios, if it's staying the same on both sides, we don't need to put it in there. And so we leave solids out of the equilibrium expression. So here's an example, nickel oxide reacting with carbon monoxide to form nickel and carbon dioxide. And so right away we're going to look at our states of matter. We see a solid, gas, solid, and gas. Gases do go in the equation, but solids do not. So they do matter. They are actually part of the reaction, but they are not going to be part of the equilibrium expression because they won't play a role in the overall ratio. And so then Kc is equal to products, so CO2, divided by the concentration of CO. So we just leave the solids out, not part of the calculation. Now, keep in mind, it does not mean that the nickel oxide and the nickel don't matter. They do play a role here. If they weren't there, this reaction would not occur. However, they do not play a role in our equilibrium expression, simply because their concentration will not change. The other thing that's left out of equilibrium expressions are pure liquids. We're not talking about aqueous things here. Okay, aqueous is salt dissolved in water. We're talking about just water. So H2O, pure liquid, would be left out of an equilibrium expression. And that's because taking amounts of water out is also not going to change the equilibrium, or not going to change the concentration. Once again, it's moles divided by liters. So if you've got a glass of water and you pour half of it out, well, you've also poured out half of your moles. And so therefore the concentration is going to stay the same. And so then, just like a solid, we can leave that out of the equilibrium expression since it doesn't change. So if we wanted to write this one out, our H2O right there, we're not going to write in our equation. So it would just be the concentration of Cl2, which is a gas, and we square that, divided by the concentration of HCl to the fourth times the concentration of O2. Alright, here it is in nice appropriate colors, so we always include gases and aqueous species because their concentrations will change with volume. However, we do not ever include liquids or solids because their concentration will not change with volume. Now, before we talk about the next part, we need to talk about a term called partial pressure. So let's say I took a sample of gas, just air. I took a jar and I filled it with air. So inside of that jar, there's going to be several different gaseous compounds. There's going to be nitrogen, there's going to be oxygen, there will be carbon dioxide, there'll even be a little bit of argon mixed in there. So each of those gases is going to be in there, and gases cause pressure. And so each of those gases are going to provide a certain amount of pressure. So let's say, for example, that the nitrogen has a pressure of 2 atmospheres inside of this jar, and the oxygen has a pressure of 0.5 atmospheres. Carbon dioxide, we'll say, is 0.1, and the argon is 0.001. And since all of these are inside of the same container, that means all of them are going to be supplying pressure to the walls of the container. That's going to be pushing against the outside, and that's what we would then feel or sense as pressure. And so if we were to put a pressure gauge on this jar and measure it, the pressure inside the jar would be the total pressures of all the gases inside of it. So something in the range of 2.601 atmospheres. And so that would be our total pressure. And then the partial pressures would be the pressure of each of the gases inside of the container. This is what's called Dalton's law. And so Dalton's law says that the total pressure of a gas is equal to the pressure of the first one, plus the pressure of the second one, plus the pressure of the third, and I can keep going on for however many gases there are inside of the system. And so what this means is that gases are easier to talk about in terms of pressure rather than concentration. So we can write an equilibrium expression that uses pressure as the measurement instead of concentration. And so we call this Kp. So we use a subscript of P, and that means it's a pressure-based constant. So we do not use brackets for this because it is not molarity, it is partial pressure and is measured in atmospheres. Of course, this will only work with reactions that involve only gases. Same basic setup, products over reactants. We've got the pressure, or whatever D is, raised to the power of the balancing coefficient for D, so on and so forth. Here's just a little bit more information on the partial pressures. They're the pressure exerted by each individual gas, and also 1 mole of any type of gas will exert the same amount of pressure. So if you have 1 mole of oxygen and 1 mole of nitrogen, even though they're different sizes, they're going to exert the same amount of pressure. And if you were to double both of them and have 2 moles of each, then you would double the pressure from each of them. And we can actually use one of our previous examples to write the equilibrium expression. So instead of Kc, I'm going to write Kp, because we're talking about the pressure this time. And the way we would symbolize this then is the P of NO. So we write a large P, a capital P, with a subscript NO, and that indicates the pressure, the partial pressure of the nitrogen oxide. and then we would square that number. And so I'm going to put parentheses around it and square, and we square just because of the balancing coefficient. And that's going to be our products, and we do that over the reactants, and so it'd be the partial pressure of N2 times the partial pressure of O2 as well. So pretty similar. The differences are you use the P's instead of the brackets and use parentheses. You still square it, still products over reactants. At times, it will be necessary to convert the values of Kc into Kp or vice versa. So if we are given an equilibrium concentration value, we can calculate it or we can transfer it into a Kp or a Kc as need be. So the way we do this is the Kp, whatever the value is equal to the Kc times R, which in this case is 0.0821 liters, atmospheres, moles, Kelvin, times the temperature, which has to be in Kelvin to match up with our R, and then raised to the power of the change in moles in gas. So we think about that example we just did, the delta N, so the change in N, remember it's always final minus initial. We ended with 2 moles of gas because we had 2 NOs, and we started with 2 moles of gas as well because we had 1 N2 and 1 O2, and so it would be 2 minus 2, so in this case it would be a delta N of 0.